Let's just be completely honest for a second about how software delivery actually feels in a lot of organizations today. I want you to picture a typical engineering team, maybe even your own. I'm not talking about dramatic, catastrophic system-down outages. I'm talking about that slow, grinding, everyday friction that makes every single release feel uniquely stressful. It's the kind of team where those bugs you swore you completely fixed last sprint somehow just keep magically reappearing in the staging environment. It's the reality where pull requests just bounce back and forth 4, 5, maybe 6 times between developers over really trivial stuff. It's the environment where your CI pipelines are constantly failing for incredibly simple, avoidable reasons, where routine infrastructure changes break things unexpectedly, and where security issues always seem to surface at the very last possible minute right before you're supposed to deploy. Honestly, absolutely everything just feels incredibly inefficient. And the worst part is, over time, this hidden friction just becomes the accepted normal for the team.
You see, most teams look at their commit frequency or their sprint velocity, and they genuinely think they're moving fast. Then they actually sit down, do the math, and realize they are spending a massive chunk, sometimes half their time, just fixing problems that absolutely should have been caught much earlier in the cycle. And when you realize that, you start to wonder, wait, are we doing this wrong? And the hard truth is, yes, a lot of teams really are, because there's a fundamental misunderstanding of what actually makes a high-performing engineering organization tick. Look, the best DevOps teams in the industry right now, they don't ship faster because they're reckless. They aren't just merging to mainline and hoping for the best. They ship faster because they have engineered an entire delivery system that intentionally catches problems earlier. They've built what we call a paved road, where doing the wrong thing is actually quite difficult and doing the right thing is completely automatic.
What we are really talking about here is the strategic, non-negotiable implementation of quality gates. Because when a reckless deployment process simply skips local checks and relies entirely on humans just trying to be really careful, it always results in a massive, unmanageable pipeline failure rate. But an engineering system that is built strictly around automated quality gates completely changes the math. And I want to be incredibly clear about what a quality gate actually is from a senior engineering perspective. Every single quality gate exists for one pure, uncompromising reason: to prevent expensive, user-facing problems from moving any further down the delivery pipeline. Think about it. The cost of a bug goes up exponentially the further it travels. A basic syntax error caught on your local laptop costs literally $0 and takes maybe 3 seconds to fix. But that exact same syntax error, if it somehow makes it all the way to production, costs thousands of dollars, completely ruins the user experience, and wastes hours of engineering time to triage and patch. Our entire goal with this modern workflow is to shift that feedback loop as far to the left as physically possible.
To really understand how this actually works in the real world, we're going to follow the journey of a single, solitary code change. We are going to track this specific piece of code from the very moment it leaves the developer's local machine, traversing all the way through to absolute production readiness. In this story, the workflow itself is the main character, not the individual tools. Because as we look at the landscape in 2026, developer experience isn't just a nice-to-have anymore. It's a massive competitive advantage. Providing a highly standardized, frictionless delivery workflow, a golden path, is exactly how platform engineering teams are unlocking that advantage. So as we follow our code change through these rigorous, automated steps, keep in mind that our goal here is not to achieve some kind of academic, theoretical idea of perfect code. Our goal is strictly about preventing avoidable, expensive problems from moving forward.
Our code change begins its journey right there on the developer's laptop, and this is exactly where the very first quality gate must exist. Before this code even has a chance to reach a shared repository, it absolutely needs to be validated. Why? Because as we said, the earlier you find a problem, the dramatically cheaper it is to fix. We achieve this early validation using local frameworks like pre-commit. Now, pre-commit is essentially a framework for managing multi-language hooks that actively identify simple issues before a commit is even finalized. It literally intercepts the git commit command, runs a series of incredibly lightweight checks, and if absolutely anything fails, the commit is completely aborted right then and there. This means the feedback happens completely locally, in a matter of milliseconds, long before the developer ever loses their flow state or switches context.
So what exactly are we rigorously checking at this local stage? We are looking at standard formatting rules, static linting, secret detection, and basic configuration validation. We're talking about running tools like Black or Rough if you're writing Python, ESLint for JavaScript, or tools like Detect Secrets to make absolutely sure you didn't accidentally hardcode an AWS API key into your file. Let me tell you from experience, pushing code to a shared CI server, waiting 10 minutes for a container to spin up and run its checks, only for the entire build to turn red and fail because you left a trailing whitespace or forgotten console log, this gets annoying quickly.
It is a massive, incredibly frustrating drain on overall developer productivity. By strictly enforcing these structural checks locally, we keep our downstream CI pipelines entirely free from trivial-style nitpicks, which saves us incredibly valuable compute resources and preserves engineering time for actual problem solving.
Okay, so once our code change successfully passes those local checks, it gets pushed up and we open a pull request. Now, if we're talking about a modern 2026 workflow, we need to fundamentally reframe how we think about pull requests. A PR is no longer just a casual place for humans to manually read through code and leave a few subjective comments. PRs are strict, non-negotiable enforcement mechanisms. They are absolute control points governed by rigid branch protection rules, required automated status checks, and very specific merge criteria. The entire PR process is designed to definitively answer one uncompromising question: can I deliver my project to production today or not? If the answer isn't a highly confident yes, the code simply doesn't merge. And frankly, with the massive influx of AI-generated code drastically increasing the raw volume of lines being submitted by developers every single day, relying solely on human reviewers to catch structural or security issues is basically a recipe for total disaster.
Which brings us right to the automated brain of this entire review process: the formal quality gate. A quality gate is fundamentally just a set of Boolean conditions based on measurable thresholds that objectively enforce your organization's quality policy. In the real world, we very often use platforms like SonarQube to act as this gate. But I really don't want you to think of SonarQube as just another vendor product you have to buy. I want you to think of it as a relentless, completely objective referee. Because let's face it, humans are subjective. Humans get tired. Humans let things slide on a Friday afternoon because they really just want to close their laptop and go home. A quality gate does not care what day it is. It objectively measures if the code is actually functionally ready to merge based on a hard, mathematical data, which completely removes the interpersonal and emotional friction from code reviews. The specific thresholds we are enforcing at this gate are absolutely critical to get right. We are objectively measuring technical debt, long-term maintainability, system reliability, code smells, duplication, actual bugs, and embedded security issues. But here's the absolute secret to making this work without grinding your entire development team to a complete halt. You must set these differential values exclusively on new code. If you take a strict, uncompromising quality gate and point it at a 10-year-old, massively complex legacy codebase and suddenly demand zero code smells, literally no one will ever merge a PR again. The entire system will freeze. Teams run into this constantly when they try to adopt these tools without a realistic strategy. The philosophy here is incredibly simple. Stop the bleeding. The legacy code is what it is, we can fix it later, but any new code that our current change introduces must absolutely meet the highest possible standard of quality. If our new code change introduces even one new critical vulnerability, the gate fails, the system blocks it, and the PR does not merge.
Now let's pivot just a bit, because in any modern system, our application code obviously doesn't live in a vacuum. It absolutely requires infrastructure. We're talking databases, complex networks, compute resources, the whole 9 yards. And the crucial, non-negotiable point here is that your infrastructure must follow the exact same strict discipline as your application code, period. If you are validating your Python or Node code with incredibly strict automated gates, but you're still letting engineers click around manually in the AWS console or push unverified, untested Terraform modules into main, you have a massive gaping hole in your delivery pipeline. Bad infrastructure validation is terrifying, because when application code fails, maybe a feature breaks, but when infrastructure fails, it brings down the entire system. Without strict automated gates on your IAC, this becomes painful at scale incredibly quickly.
So as our code change, which let's say also includes a necessary infrastructure update, moves forward, we hit the infrastructure gate. If your team is using Terraform, this validation journey starts locally with simple formatting using Terraform fumped, and then it moves to Terraform validate. Now, what's incredibly crucial to understand here is what validation doesn't do. It does not talk to your cloud APIs, it does not generate a state plan, it is purely the first fundamental structural gate. It basically parses your local TF files, it verifies your argument names and types against the local schemas, ensures all required attributes are physically present, and strictly checks your module wiring. It simply answers, does this configuration even make structural sense to Terraform? But of course, structural validation isn't enough to merge. Long before we ever generate a Terraform plan to see what resources will actually change in our cloud environment, we absolutely must run this infrastructure code through dedicated infrastructure as code security scanners. We're talking about tools like Checkoff, TFSec, or Terrascan. These tools are designed specifically to catch misconfigured, completely open S3 buckets, overly permissive security groups, or hard-coded database passwords before those resources ever get provisioned in reality.
If you're enjoying this deep dive, consider liking the video and subscribing to DevOps Corner for more DevOps and infrastructure content. All right, so let's recap where we are. Our code has successfully passed all local checks. The PR quality gate is completely green. Our infrastructure changes are structurally sound and highly secure, and the code has finally been merged into the main branch. Now it enters the continuous integration pipeline. This is where the real heavy lifting happens. But a pipeline is truly only as good as its fundamental architecture. Bad, poorly designed pipelines waste an incredible amount of precious engineering time. The specific ordering of these verification stages is absolutely crucial for your team's velocity. You must design your CI pipeline to fail as fast as humanly possible. This means we run the fastest checks right up front, redundant linting and lightning-fast unit tests. Only if those pass completely do we move on to the expensive, highly time-consuming stages, like building the heavy container artifact, running deep, comprehensive security scans, and executing those complex, notoriously slow integration tests. Whether you are packaging a Node.js backend, containerizing complex Python microservices, or preparing deployment manifests for Kubernetes, the golden rule is exactly the same: fail fast. If a core unit test is ultimately going to fail, we want the developer to know in 2 minutes, not 45 minutes after they've sat around waiting for an entire test database to provision. And embedded incredibly deeply within that CI pipeline is our next major, completely non-negotiable gate: automated security scanning. Look, we are way past the days where security is just some afterthought that gets handed off to a completely separate siloed team right before a major launch. Rising security expectations across the industry mean we must use automated tools like Trivy, Snike, or GitHub Advanced Security to execute relentless, continuous scanning at every step. And we aren't just scanning one single thing here. We are running comprehensive static application security testing, or SAST, directly on our source code. We are deeply scanning the underlying OS packages in our Docker images, whether that's Alpine, Ubuntu, or RHEL. We are running continuous dependency scanning on every single NPM, Maven, or Go module that our developers pull down from the internet. And we are running automated, highly aggressive secret scanning to ensure absolutely no API keys or tokens leak through the cracks. If our code change happens to introduce a container image with a known critical vulnerability, the CI pipeline fails immediately. The gate holds strong, and the bad code does not move forward.
I actually want to pause right here and deliver a very strong, heavily opinionated thought, built directly from years of real production experience. Security in 2026 is not about compliance. It is not about risk management theater, where we force engineers to sit in a change advisory board meeting and manually review a spreadsheet just to check a box for some external auditor. That approach is brutally slow. It is highly prone to human error, and frankly, it doesn't actually secure the underlying system at all. Modern DevOps security is purely 100% about risk reduction, and true risk reduction is achieved exclusively through automated, continuous, and ruthless enforcement right inside the delivery pipeline. Finding a vulnerable, outdated dependency while the code is still sitting in CI is incredibly cheap and extremely fast to fix. Finding that exact same vulnerability months later, after it has already been deployed to a live production environment, is exponentially more expensive and infinitely more dangerous to the business.
Let's actually zoom out to the much bigger picture for a moment and look at the actual science behind why we relentlessly structure our software delivery exactly this way. There is a core principle that perfectly illustrates the reality of modern engineering, and it goes like this: speed depends on stability, so good IT practices give you both. For a very long time, our industry genuinely believed in this concept of bimodal IT, this pervasive myth that you basically had to choose between moving incredibly fast and breaking things, or moving incredibly slow and being perfectly stable. The data unequivocally proves that it's completely false. The highest performing engineering teams do not trade stability for speed. They achieve incredible, sustainable, long-term speed entirely through relentless stability. And that rock-solid stability is built entirely on the automated workflows and the rigorous quality gates we've just walked through today. Real DevOps is not simply about going out and buying the most expensive new CI tool, and it certainly isn't about automating a bunch of chaotic, undocumented bash scripts. It is fundamentally a philosophy of pure risk reduction. From the developer's very first local pre-commit hook to the strict, uncompromising PR merge rules, from SonarQube's highly objective code measurements to Terraform's rigid structural validation, right through to the automated container security scanning in CI. Every single quality gate we have discussed today exists for one reason: to protect the end-user experience.
By implementing deliberate, automated, highly controlled friction very early in the development process, we completely eliminate the chaotic, extremely stressful friction that plagues so many teams at the very end of the process. Our single code change finally made it to production smoothly today, not because we rushed it, but because our system explicitly verified its safety at every single step of the journey.
Ultimately, the most effective workflows are the ones that consistently catch problems before they become expensive. So I want to leave you with this final thought. If you were to honestly audit your own team's delivery pipeline today, how much of your daily speed is just an illusion built on a mountain of technical debt, and how much of it is actually built on real engineered stability? If you found this helpful, make sure to like the video and subscribe to DevOps Corner for more deep dives like this.